Hello, today we're going to be talking about rectangular area moments of inertia via the second moment integral. So the first thing I'm going to do in this video lecture is to talk about why we would want to find this particular mathematical value. So this is dealing with bending. So usually what we call the rectangular area moment of inertia is the second rectangular area moment integral of some shape, usually the cross section of a beam that we're subjecting to bending loading. And this value is useful in engineering mechanics because it offers a quantitative measure of that shape's resistance to bending moments. And that's going to help us relate moments that are applied to some beam to the stresses that we experience within the beam. So if we have some beam and we apply some bending moment here, I've just got a simple rectangular cross section over here. I have something called the neutral surface, which I talk more about in the bending video lectures. And that neutral surface is where I have zero stress. And so on one side, I've got the bending moment over here, the internal stresses over here. I've got some compression stresses over here counteracting the top part of that bending and some tension on the bottom there. And so this diagram shows the distribution of those internal stresses. All right, and so we're using the second moment integral here. Because the shape's resistant to bending, we have kind of two parts to this. So we need to counteract this moment, and the sum of all of these little forces, each of those is going to exert a little bit of a moment about this neutral axis point. And so if we sum all those up, they have to be equal and opposite to this applied load to our piece. And if we have a moment, there's two parts to it. It's force times distance. And that's where the second moment integral comes from. And so the first part, moving up or down from the axis, the distance increases. And so obviously the moment arm is increasing there. That's part one. And we can also see that the force is getting bigger in a linear fashion the further I go from the neutral surface. So if the moment is the force times the distance, force is increasing with distance, and the distance is increasing with the distance. And so we have a d squared term for our second moment integral. The further the square of kind of this distance is contributing linearly or contributing to the kind of importance of that point. All right, so starting from the basic equation for a second moment integral, we're going to be integrating over the area, this d squared term here. All right, so we need to be able to kind of relate this and plug in some actual numbers. So if we do that, in this equation we're moving out from some axis. That could be the x-axis or the y-axis. It really could be any other axis in between, but usually we're just going to deal with horizontal and vertical axes here. And the distance represents some point's distance from that axis. So it could be further up, further down, it could be further to the left or right. We just need to be able to measure that distance value there. And generally we set it up so that we have the shape that we're looking at. The centroid of that shape will be the kind of point where the neutral axis and the x and y directions come together. And we put the origin point at the centroid. X-axis goes horizontal, y-axis goes vertical. All right, so when we do that, we're going to have two different axes. So if the neutral axis is the x-axis, it's the horizontal axis, we're going to call that moment of inertia Ixx, or the moment of inertia about the x-axis. And for the y-axis, or the vertical axis, we're going to call it Iyy. Note that these aren't necessarily the same numbers. And that can be seen in kind of different shapes, resistances to bending in different directions. So if I've got something like this folder, it's pretty thin. It's really easy to bend kind of in this, about the neutral axis would actually be the x-axis, horizontal. But if I think about bending this kind of out towards you or towards me, I can't really bend it that way. It's got more resistance to bending in that direction. And so Ixx and Iyy are going to be different values. There's more than one moment of inertia. All right, so for Ixx, the distance or d squared term is going to be distance from the x-axis, and the distance from the x-axis for any point is simply its y-coordinate. And so we're going to end up with y coordinates in Ixx And vice versa, for IYY, the distance from the y-axis for any point is simply going to be its x-coordinate. So we're going to end up with x coordinates in the IYY equation. We put these together in our specific equations. Ixx is going to be from y min to y max, dA times y squared, and Iyy, going from x min to x max, is going to be dA times x squared. This is a little bit counterintuitive here, but this is those distances. Distance from the x is y, and distance from the y is x. All right, and here I've got a diagram showing Ixx. So this moment of inertia about the x-axis going across the entire area, so dA integrating over the area. If I go from some minimum y value to some maximum y value, so I'm going from the bottom of the shape all the way up to the top of the shape, and these might this might be general numbers, it might be specific, it might be like 2 inches, negative 2 inches to positive 2 inches. I need to multiply by dA, and dA is the rate at which the area is changing as I move from the bottom up to the top. And so if I think about that, dA is kind of the area of this little rectangle that I have at any particular value of y. And so as I move up, the area of that rectangle is going to be the width of the rectangle, and the height is going to be this very small value dy. And so we're just going to put dy, the equation describing the width times dy, and this equation describing the width at any one point. You'll notice as I move from the bottom up to the top, the width of my kind of shape is changing as I move up. And so I'm going to have an equation rather than just a specific number in there. All right, so I take that equation for the width times dy, I multiply that equation for the width times y squared, take the integral, and if I have actual numbers in here, I'm going to wind up with a number for Ixx. You should wind up with some, the way the integral works, you're going to wind up with some kind of distance to the fourth, so it could be inches to the fourth, meters to the fourth, millimeters to the fourth, something like that in your final answer. So if we look at Iyy, this is the moment of inertia about the y-axis. We kind of flip everything. And so now rather than moving bottom up to top, we are moving left to right here. And so as I move from some minimum or leftmost point to some rightmost point, I'm going to multiply, I've got my dA equation, and so dA is the rate at which the area is changing again. And so if I think about the rate at which the area is changing, kind of the area of this little sliver, the dA, is going to be the height at any one point. And so I need to find an equation describing the height of my shape at any particular value of x. And I multiply that by dx, which is the kind of width of my little sliver there. All right, so the equation for the height times dx, I take whatever that is, that mathematical function, multiply it by x squared. I take the integral, and I'm going to wind up with Iyy in my equation. And so this is kind of the brute force integration method for finding moments of inertia. All right, so when we want to find moments of inertia, you probably will do some moment integrals, but there's other methods available as well because this is such an important part of these bending calculations. And integration is the basis for all of the methods. The two other methods I want to mention. You can also use something called the method of composite parts with the parallel axis theorem to calculate moment integrals. And that is just combining adjusted moments of inertia for simple shapes. So if you have a couple different simple shapes, you've got like an I-beam, it's going to be two rectangles connected by another rectangle in the middle. So each of those rectangles is a simple shape there. And if we combine those together, we find the moment of inertia for a more complex shape there. And I also can use, so we can also realize though that if I look up these moments of inertia, I'm looking them up in a table, and those tables are generated via integration. So someone else is doing the integration for you there. There's also software-based calculations, so most CAD software packages can calculate these moments of inertia. And all you're doing there is passing on the integration to the computer. So the computer does this integration in the background, and really the moments of inertia are always going to be based on integration in some way, shape, or form. Alright, so that's all we have for today's video lecture. Thank you for watching, and I hope to see you again.